It to Duluth Sandstorm, I think it's worth it.
Okay, here we go. So let's see, number one. Describe in words the motion of the four walkers shown by the four lines in figure 5.4. So this has to do with a lot of the motion diagrams we talked about recently. 5.4, where is that? Right there. Okay, I'll make it big. Okay, everybody sees that? All right, so what do you think, Michaela? Give me A. What is walker A doing there? Good. Constant speed, right? And how do we know that?
It's a straight line.
It's a straight line, but what about the straight line?
It goes.
Okay, it's got. Well, I guess if it's a straight line, it implies it has a constant slope. So there you go. Very good. Very good. Okay, let's see, Peter. How about walker B? Actually, why don't you add one more thing to walker A? He's walking at constant speed, and where is he starting? Okay, so he's starting at 0, which they say is High Street. He's starting right. Does that make sense? Okay. He's walking east on High Street. Okay, so Peter, back to you. Walker B, what's he doing?
I don't know.
Walker B is slightly west of High Street, place passes High Street.
Okay, so he's starting, like let's say, so for you guys, this would be like east, right? Just pretend. So he's starting back there at a negative value, right? He's west of the beginning, and he's walking at constant speed to the east, right? How do we know those two things? Okay, because of his starting point, because he starts at a negative value, right? And it's a straight line. Okay, very good. All right, Caleb. What about C?
C walks west, like fast and in the beginning, but slows to a stop.
Perfect. Okay. Walker C starts at the beginning, but walks in the negative direction, in the west direction, starts off walking pretty fast, but then gradually slows down. And how do we know that he's slowing down?
Because the position doesn't change.
Okay. Because what?
Position doesn't change.
Because, well, okay, the position doesn't change very much. We can look at the slope of this thing, right? The slope starts off being steep and negative. Steep slope means fast, right? The fact that it's negative just means backwards. And then it levels out. And the slope gets less severe. It gets to be a smaller number, right? Small absolute values. Good. Let's see. Austin, what about D?
He's just slowing down at a constant rate.
D?
Yeah.
Why slowing down? Okay, now this is a position time, right? So now think, speed has to do with slope. He's walking west. Does the slope ever change?
No.
And the slope corresponds to speed, right? You might have been thinking about this as a velocity time graph, but it's position time graph. So adjust what you said, maybe just a little bit.
So he's walking west at constant speed.
There you go. Walking west at positive speed, and we know that because the slope is negative. Where's he starting? East. He's starting a little bit in a positive value, so he's starting to the east and walking by High Street to the west. Very good. Okay, so number 2, is that the next one? I think. Is that right? Yeah. Describe the motion of the car shown in figure 5.5. Ooh, that's a big one. Okay. Car in 5.5. Sam, what do you think?
He said the car travels backwards 20 meters for 10 seconds.
Okay.
Stops for 20 seconds, then goes forward 50 meters for 20 seconds, and returns backwards for 30 meters for 20 seconds.
Perfect. Perfect. So it starts off traveling in the negative direction at constant speed. We can even see how far it goes, right?
Yeah.
You can see like where it ends up after so much time. Pauses for a while. Then it goes forward, turns around and goes forward for a while, positive, constant speed, and then it turns around and moves back to the origin, and then it just parks and rests there a bit.
Well, actually, wouldn't it not have turned around, because that would require some.
Well, okay, yeah, so technically this is impossible, because but you understand, I mean, when I say that, I'm just being a little bit, we're going to simplify this a little bit, but you understand physically, you couldn't do this. You couldn't go from instantaneously having some positive constant velocity to some negative constant velocity in no time, right? There would have to be, physically, there would have to be kind of a rounded nature to that. Or it would, it's just impossible. Or anybody in the car would have been smashed into the smithereens. Right? So acceleration would have been too high.
Have we done that before? Like human?
Wait, what if you were,
It can't, it's physically impossible because the car has mass.
what if you were going forward, it's like you got launched backwards?
Okay, but even then, even if you get launched backwards,
There's still gonna be a point in time when you have zero.
yeah, there still has to,
Well, you can't go faster than speed of light, but like, if you can't have no stop.
okay, good, good.
Yeah. Yeah.
All right, let's see. Oh, back to business here. Whoop, whoop, whoop. Well, actually, maybe you have something to add to it. Anybody else want to add anything to that? No?
Can light accelerate, can light do that?
Light can, but light has no
It
rest
has
mass.
no mass.
Yeah.
Right, yeah.
Yeah.
That's weird.
Yeah, so
That's
any,
gravity.
okay, so, good question. I'll give this a second. Light can instantaneously change directions because light has no mass, right?
That's
But
right.
any object, even an electron, any object that has mass could never do this. Could never do that. Okay, it would require an infinite force, which the universe can't provide.
Wait, so what's light made out of?
Light is made from photons.
So photons don't have mass.
No, photons have no mass, but we haven't talked about momentum yet. Momentum is related to mass though, and photons have momentum.
So they have an impact, right?
Yeah, they do.
So that
They
means,
do.
and that if we had flashlight in space, if we had, well, maybe not flashlight, but some insanely large light
You mean
system.
like a solar sail?
Sure. Is
Yeah.
that what? Oh, nifty.
Yeah, there's
Yeah.
that's actually conceivably a way that people could travel
Well, aren't solar
large
sails
distances.
just like, taking the particulates that are like shot out from the sun, or is it just light?
No, the particulates go right through. It's the light. It's reflecting the light. Yeah, it's just a solar sail would just be a huge piece of mylar, silvered mylar, and it would just have a wet, kind of a netting on it, and it would be all the photons leaving the sun would reflect off of this, and they would transfer their momentum. Which we'll talk about this in more detail in a few chapters.
Did you know that that's how Count Dooku's ship works?
Oh, okay.
Not a joke.
Yeah. Okay. So let's see. Moving on to number three. Let's see, Hagen. How about figure 5.5? I want to know when exactly was the car 20 meters west of the origin? From B to C. Okay, so from 10 to, what is that, 10 to 30 seconds after it started, car's going to be at rest 20 meters west of the origin. Good. Where was the car at 50 seconds? Nathan, what do you think?
30 meters east.
30 meters east. Very good. Okay. Everybody sees that? Questions? Throw your hand up if you got a question about any of these. The car suddenly reversed direction. When and where did that occur? Suddenly reversed direction. Where's that? Let's see, who are we calling on here? Elijah, where'd that happen? At what point did the car suddenly reverse directions? Say it again? D. Yeah, there you go, D. So at point D, the car reversed direction. Okay, so this brings up sort of an interesting dilemma here. What does it mean to be a moment in time?
About the position you're at, specific. Because don't they put like all these different moments together, and that makes time.
Okay, interesting. So this is and we'll kind of, it's on you guys you might want to just jot this note down, future discussion. And we'll come back to these if somebody carefully catalogs these, because we'll come back to this later. But for now, I want you to just start.
I'm on it.
That's all river, right?
That seems like a good river.
I know.
It does.
So the question is, what is a moment in time? And it's a good answer. Kate's saying, okay, a moment. If you stitch together all the moments in time, then that creates a timeline. Sure, and that would be like a video camera, right? Each moment is a frame. Okay. Okay, but then that brings up the question: how long does a moment last?
One.
One moment.
Well, would it be like a picture, could capture
But a
not an
picture-
exact moment in
But a
time,
picture isn't an
and-
exact moment, it's a brick, it's a time.
Okay, this might seem like kind of a futile question, but it's actually really interesting.
I said like a picture.
Like a
Okay, so
picture
let's,
of.
okay, now we got good.
There
Now, I gotta see hands here, you gotta raise hands so we can like organize this participation. So a moment is, Scott, what do you say?
Like a picture, it captures that specific, like that specific spot and nothing else.
Okay, so it's like a picture. Now, if you've all probably seen or done like a little animation thing, right, on your grade school in your notebook where you draw a little
Yeah.
stick figure that moves across and right, you flip the papers down and you can
Yeah.
see the animation. Or if you're looking at individual frames of a movie, then a good model for a moment in time would be it's one of those frames that you're gonna stitch together, right?
How many frames per second are there?
Okay, that's the thing though. Frames go by, if you watch a movie, frames go by at 30 frames per second, or if it's really a good quality, it's 60 frames per second. Okay, so how many moments per second are happening then for reality to progress forward as we know it? Okay, raise your hands. Oh, here we go. What we got? What do we think?
Is it possible to tell?
Like what Kate said, it is not.
Yeah, okay, that's, I mean, there's really, probably the best answer is an infinite number, right? Because how can you separate a moment? And yet we talk about moments a lot in physics. We'll talk about, for example, if we throw a ball up in the air, the moment when it's at the apex of its trajectory, right? But keep in mind that even though we think of it as a picture, this illustrates a point that I talked about, a month ago, but it illustrates it pretty well. Physics is awesome, it's interesting, it models the way things really work, but remember that it too is all based on math, and math is essentially 100% made up, right? There's nothing about it that's exactly realistic, it's just a good model for understanding the way things work. And the strength of a physics model is not based on whether it's reality or not. It's based on how predictive it is, how well it works, right? Even thinking about something like a moment, a picture, it's a good idea, but even a picture is not a moment because a picture requires some finite shutter speed, right? Because how does it work? There's some film, there's some light-sensitive medium on the film, and some photons, some light has to strike the surface of the film to cause that photosensitive film to change, right? And so, technically, if the moment is infinitesimally short, then that's not time for even a single photon to strike the frame, and you could never actually have a picture.
Do photons move at the same speed?
Photons all move at the same speed, which is the speed of light.
So wouldn't you be able to theoretically categorize a perfect picture as one layer of photons?
No, because photons
In a
are
theoretical sense.
don't specifically exist in one place or one time. Photons,
one layer.
and so the answer is, I don't want to this gets kind of weird. And I don't want to just, we could go off on it, we could talk about this for hours and see interesting discussion, but the point is, just recognize that a moment is kind of an artificial construct, right? It's something we all recognize what it is, but that itself is a physical model that we just all intuitively understand. We're pretty familiar with time. And when we say something like the moment when the ball is at its highest point, we all know what we mean, but even that, as obvious as that seems, and as straightforward and concrete, even that is really, it's really not realistic, right? Okay. Let's see, moving on, let's see, now we're up to page,
So, for my cataloging of this.
Yeah.
What exactly, because like right now I just have what is a moment in time, but you kind of seem to already touch on that.
okay, so here's the discussion we'll eventually have. Is time granular?
Granular?
Mm-hmm.
Okay.
Is there, in fact, a smallest moment in time that you can have? Okay, and we'll talk more about that later in the year.
I actually have a question. Okay, so if you have an island, if you measure the outside of the island in feet, you'll get a certain distance. But if you measure in centimeters, you'll get a longer distance because you can be more precise.
Mhm.
How, does that mean that the island has an infinite perimeter?
Okay, put that down for future discussion because they're related.
Okay.
I'm not going to answer that now,
Okay.
but there is actually an answer to it.
I've never thought about
Yeah.
Seriously.
That's a very good question.
That's so weird.
Okay, so
Yeah, exactly. It's a flexible ruler. What do you mean by flexible?
Wait, what about
I put a foot.
River, what about high tide and low tide?
Oh.
That's that into account.
Yeah.
That's actually-
I mean, yeah.
No,
So
river.
true.
I know.
Yeah, I think calculus is almost
Okay.
same time.
Or is this
I was afraid this was gonna be hard.
Oh, okay.
All right, let's see, number 8. Number 8. So I want you to, everybody, if you haven't done this, get out and do this right now. Draw a position time graph of a person who walks 1 block at a moderate speed, waits a short time for a traffic light, walks the next block slowly, and then walks the final block quickly. All blocks are of equal length. Well, what's that going to look like? What's that going to look like? So we go. What do you think? Who wants to draw this? You want to try it? Just try it.
Oh, go try it.
They'll help you out.
It looks good. Go try it.
They'll help you out.
Yeah.
Okay, so I should label something. Let me do this for you real quick. So this is going to be T, and this is going to be D. Okay?
Will you read it to me?
Yeah, you bet. Okay, so it goes. Yeah. It goes. I'll move this over here. So it says, walks 1 block at a moderate speed. Okay, good. Waits a short time for a traffic light. Good. Okay, walks the next block slowly.
That's too fast.
There we go. Okay. And then walks the final block quickly. Okay, good. Now, excellent. If all blocks are equal length, there's one little thing we'd have to change here. What would that be?
Would you have to change, okay, so the third line, would the third line have to be more up straight and the last line would have to be?
No, the opposite.
The opposite.
Okay, I'm not.
Wait, the third line needs to be kind of flatter.
Because we said. Okay, let's switch. Okay, we said moderate, slow, fast, right? But we said all blocks are equal length.
When you say block though, do you mean like a street block or
Yeah,
like
street
each
block.
section? Because like when she waits at the light, is that a quote block?
No. The waiting at the light is arbitrary. But the other ones, when she's walking along the street, we're saying the physical length of the blocks that she's walking are all the same.
Make sure all 3 of the other lines, not the straight one, but actually make sure all the other ones are even.
Okay, yeah, so what's gonna be the same about all these lines? Okay, the displacement's gonna be the same, right? So it's very, very close. We would say probably, maybe it'd look like this more, slightly. So the first one is moderate, so we're gonna go up to this height, right? Because that's 1 block, that's 2 blocks, that's 3 blocks, right? So the first one, we're gonna go at moderate speed up to 1 block, and then we're gonna rest for a little bit, and then we're gonna go slowly 1 more block. So now I gotta go up to this distance, or this position, right? More slowly, so that's gonna mean something like that, right? And then the last one, we're gonna go up to this position over a shorter period of time, so that one's gonna be more like that. See what I'm saying? Okay. Yeah, I don't know.
Oh, no.
Okay, how about this? 8, so now what are we up to? Oh, were those the ones that were, I was looking at the wrong ones, wasn't I?
Oh, I see what you
I think it was still fun.
Yeah, it was fun. Page 87. Oh, no, I didn't. That was right. Now page 89, sorry, 89. We've got 9 through 12, all of these. Okay.
Yeah.
So, Lincoln,
Yeah.
consider the motion of bike rider A in figure 5.7. Write the equation that represents her motion. Where will rider A be at 1 second? So we gotta go back to 5.7. Right there. No,
This is the slope we want.
where's 5.7? That's it right there?
Yeah, that one right there.
Okay. Oh, yeah, and which one was it? A?
Yeah.
Yeah, so what's gonna be the equation for the position of rider A?
The equation,
The
what's this gonna be? It's just slope, isn't it?
Well, it's a line, right?
Yeah.
Okay, so it's gonna, slope's gonna be a part of it.
Yeah, so
What's the slope? It's just. So are we going to?
Okay, well, no, we just want, we want the, that, rider A, that is their motion diagram, right? So we wanna write the equation of that, but what do we have instead of y and x? What is our independent variable, our input variable instead of x?
T.
T, okay. So we're putting a t in for x, what about y?
M,
D.
D.
So what we've really got then, instead of y equals mx plus b, ours is maybe gonna look something more like, right here.
Plus B.
D as a function of t, t's the input, equals m, well what's m gonna be? What is it?
Maybe ask this.
1 over 4.
Well,
Oh, yeah, 1 over
1
4.
over 0.2.
Okay,
No, 2 over, yeah, 1 over 0.1.
okay, so we have to do a rise over run, don't we? Right? If we're gonna calculate the slope, we need a slope triangle, let's just use those 2 points right there. I'm gonna rise by positive 2,
And run 0.2.
run by 0.2.
Yeah.
Okay? So we get positive 2 meters over positive 0.2 seconds. Well, 2 divided by 0.2 is 10. So we get 10 is our slope times t plus what's the, what we would call the y-intercept would be the d-intercept for us. What's the start value? Negative 2. So, oh,
10T. I like it. Right? So you just go
10t minus 2. Okay? Make sense?
Is that just physics slang for 100? 10T? Like 10, like 20? But technically?
Oh.
4T? 14?
Oh boy, I don't know. Where's the hook?
Like 6T? 60?
Yeah, you can quite have.
Okay, yeah, we got it the first time.
Oh, sure, no one was laughing.
Yeah.
I wonder why.
We were busy doing it.
Okay, so where will the rider be at 1 second?
Yeah,
Exactly.
it's gonna be long.
Okay, so
0.3 seconds and it's gonna be at 1 meter.
okay, so everybody agree? A, if we project that forward, if we move, and we could use the equation we just had, right? We had the equation. 2 ways we could do this. We could use the graph, or we could just input a value into the function, right? We had d of t equals 10t minus 2, right? And so if I'm going to evaluate that at t equals 1, all I'm doing is plugging in 1 per t. What do I get? D of 1 equals 10 minus 2 equals 8. Does that make sense? We could extrapolate the graph forward though, and if we did, I guess we'd see that probably that's 8 right there, and so, right? But that's better.
Oh, nice.
Okay. All right. Getting there. Okay. Ian. Sound pretty enthusiastic about it. Okay, consider the motion of bike rider C in figure 5.7. Okay, same issue now. We've already done this once, so this is gonna make it a little easier. For C, what's gonna be the equation of motion for that bike rider C? We wanna know position as a function of time.
Well, so the slope's
What's that gonna be? So we're gonna calculate the slope. Here's how we could calculate a slope triangle, right? So what's our rise? What's our run? Okay, so then our slope is -4 meters over 0.6 seconds. What's that reduced to? Hey, you're too much talking. Okay, so what would we do here? We don't want to have a decimal on the bottom, so let's do a little mental math. Mental math is important. This is good to know for if you want to like do some free brain strengthening. Here's one way to do it. Algebra is great for strengthening your brain. It's like lifting weights with your hand. It encourages you to build lots of those dendritic axonic connections. But it's been shown that doing mental math.
That's a period.
Yeah, what does it do?